Today we're going to talk about oxidation numbers. So oxidation numbers are the number that we assign an element based on the difference between the positive protons and negative neutrons. So remember, elements like to gain, share, or lose, so they have an octet to become stable. So if you'll recall, metals like to lose them and they revert to a smaller shell and they have a full octet. So they tend to be positive or cations. Nonmetals tend to gain them to fill their outer shell to have 8, so they tend to form negative ions. Therefore, you have electrostatic attraction between them and their numbers cancel out and you form a neutral compound. The same is true when two nonmetals bond and they have overlapping orbitals. They share pairs of electrons and that makes a neutral compound. So today we're going to look at some other special rules about oxidation numbers, because determining the oxidation number of elements helps us in formula writing, compound naming, and when we cover oxidation reduction reactions. So the oxidation number of an atom is 0 on a neutral substance that contains atoms of that element only. So for example, oxygen, ozone, phosphorus, and sulfur, which occur as O2, O3, P4, and S8, and aluminum will all have an oxidation number of 0 when by themselves. The oxidation number of simple ions is equal to the charge on the ion. The oxidation number of sodium is +1, and the oxidation for chlorine is -1. The oxidation number of hydrogen, this is important, is always +1 when combined with nonmetals. This is very important. Hydrogen can act like a nonmetal and covalently bond with other nonmetals, but it can also lose an electron and act like a metal and ionically bond with other metals. So this is important. So when hydrogen is combined with other nonmetals, it's +1. But it's -1 when bonded with metals, like as in lithium hydride, sodium hydride, calcium hydride, and lithium aluminum tetrahydride. The metals in group 1 form compounds such as lithium nitride and sodium sulfide, where the metal has an oxidation of +1. And we already knew that from previous lessons. So group 1 +1. Because it has one valence, loses one, now it has one less electron than protons. Elements in group 2, like as in magnesium nitride, calcium carbonate, have oxidations of +2. It has 2 valence, loses 2 valence, now it has 2 less electrons than protons, it has a +2. Aluminum is always +3 when combined with other elements, unless it's by itself, then it's 0. Oxygen, this is important, although I'll never use the exception. So for all the oxygens you'll be exposed to, unless you're talking about a peroxide or an oxide, it'll always be -2. So it's in group 16. Its most common oxidation state is -2. Elements in group 17 often form compounds like as in aluminum fluoride, hydrochloric acid, zinc 2 bromide, in which the nonmetal has an oxidation of -1. Typically, the halogens have a -1 oxidation. That's its most stable oxidation number. The sum, this is very important, the sum of the oxidation numbers in a neutral compound is always 0, such as in water. So if we have 2 hydrogen atoms, which each have a +1, because it's combining with oxygen, which is a nonmetal, and one oxygen atom has a -2, then the sum of those is equal to 0. The sum of the oxidation numbers in a polyatomic ion is equal to the charge. The oxidation number of the sulfur must be 6 in order for the sum of the oxidation numbers of the atom to equal -2. So sulfur has to be +6 because each oxygen in SO42 is equal to -2. So 6 minus 8 equal -2. Elements toward the bottom left corner of the periodic table are more likely to have positive oxidation numbers than those toward the bottom right corner of the table. Sulfur has a positive oxidation number in sulfur dioxide because it's below oxygen in the periodic table. So the oxidation numbers of the polyatomic ions that you've seen before are the little superscript numbers. So the sum of nitrogen and hydrogen together equal +1. The sum of 2 carbons, 3 hydrogens, 2 oxygens equals -1, and so on and so forth. Then don't forget about the common cations of the transition metals, which have variable oxidation states because they have those electrons and those d orbitals. And we'll be using them to help us figure out how to write formulas and how to write names. So let's do some examples. You can stop this at any time. You will need a calculator, scratch paper and pencil, and if you have it, your periodic table that you wrote the oxidation numbers on. So we're going to look at what is the oxidation number of the atom nitrogen in the compound called sodium nitrate. So we're going to make that our X value. Okay. Well, I know from rule 1 or rule 5 that group 1 has a +1 oxidation. We're going to make in our X. I know that oxygen, unless combined in oxides and peroxides, is -2. And I know that the sum of the oxidation numbers equals 0 because it is a neutral compound. So the sum of the oxidation numbers is 0 because it is a neutral compound. How do I know it's neutral? Because it doesn't have a little superscript up here. So as long as it doesn't have the superscript up here, then you know that it's neutral. Okay. So now I'm going to just make this a nice algebraic expression. It looks a little different than most algebraic expressions because we want to keep track of the positives and negatives. So I know that sodium is +1 plus X for nitrogen. I have 3 oxygens. The subscript of 3 becomes the coefficient of the oxidation of that element. So then solving, we end up with 1 plus X minus 6 equals 0. Gathering like terms, we end up with X minus 5 equals 0. Solving for X, you end up with X is equal to +5. Sorry I don't have those other steps in there. If you were in person, I could be showing it to you on the board. All right, let's look at the next example. We have the nitrite polyatomic anion, and we want to figure out what is the oxidation for nitrogen in this particular ion. Well, my nitrogen is going to be my X. I know that oxygen, unless in peroxides and oxides, is -2. I know that because of the sum of the oxidations of nitrogen and oxygen equal the oxidation number on this polyatomic, I'm going to set these things equal to -1. Since I have, this is X, I got it in different order, sorry. Since I have 2 oxygens and each one's -2, then this is -4 plus X equal -1. I'm going to solve using algebraic expressions, so then I end up with, this is -4, I'm going to add 4 to both sides, adding 4 to both sides, we end up with X is equal to +3. So we have this compound, we have potassium 10 hexahydroxide, 10,6 hydroxide. So we're finding what's the oxidation for 10. So if you'll recall that potassium's in group 1, so it has a +1. We don't know what 10 is. Now we have a polyatomic ion. This whole thing has an oxidation of -1. So if you'll look at your polyatomic ion sheet, you would see that hydroxide by itself has an oxidation of -1. So this is really oxygen covalently bonded to a hydrogen. You don't know how to write these yet, but I'll write it for you anyway. And we got these extra electrons sitting around here, and the whole thing has a -1 charge. So we treat the polyatomics like one thing. So if you have to, just think in terms of the charge of the polyatomic. So that's -1, and there's 6 of them. So oxygen's -2, hydrogen's +1. Since we have 6 of those, you can just treat them all as hydroxide -1. Combining them all together, you can either separate them if you want to, or you can combine them all together. Either way, doesn't matter. You end up with the same answer. So here I've separated them. You can combine them and say 6 times -1, or you can do it this way. So we end up with 2 plus x minus 12 plus 6. So we end up with x is equal to +4. Gathering like terms, we end up with -12 plus 6 is 6, and then -2, we end up with +4. Calcium nitride. What is the oxidation state of the nitrogen in calcium nitride? Well, calcium is in group 2, so it has a +2 charge. We don't know nitrogen. We know the sum of them is equal to 0 because it's a neutral compound. I have 3 calciums and 2 nitrogens. So this ends up being 6 plus 2x equals 0. Subtracting 6 from both sides, we end up 2x is equal to -6. Dividing by 2, we get x is equal to -3. So we have perchloric acid. We're looking for the oxidation number of chlorine in perchloric acid. Well, recall that hydrogen, when combined with nonmetals, is equal to +1. We don't know what chlorine is, and we have 4 oxygens, each being -2. So setting them equal to 0 because it is a neutral compound. So we have 1 plus x minus 8. Gathering like terms, we have x minus 7. Adding +7 to both sides, we find that we get x is equal to +7. We have calcium phosphate, and we're trying to find what is phosphorus oxidation in calcium phosphate. Calcium is in group 2, it has a +2 charge. We don't know what phosphorus is, and we know that each oxygen is equal to -2. Since we have 2 phosphates, that means we have twice as many of each kind of element, so you multiply subscripts. So in this case, if you need to, you can pretend like phosphorus has a subscript of 1, even though we don't write the 1. So 2 times 1 is 2, and 2 times 4 is 8. So we end up with 6 plus 2x minus 16. 16, gathering like terms, 16 and 2. And then dividing by 2, you end up with phosphorus is +5.